Let us start with the last talk for today's activity. Professor Jason Gaddis, Miami University, will talk about rigidity of quadratic Poisson algebras. Welcome.
Thank you very much for the introduction, and thank you for to the organizers for having me. Also, thanks to the organizers for not scheduling me at 2 a.m., which is when this conference started for me. So unfortunately, I missed some of the early talks because I was asleep. Okay, so I thought actually I'd start because the name of my university causes immense confusion, even here within the States, because down here in Florida, there is a very famous Miami. There are, for example, rap songs about it. And there's also a very famous university, which is the University of Miami, which is not where I am. I am up here. This is Ohio, and Miami University is right here, and so understandably that's very confusing. My understanding is the two don't have anything really in common. Both areas are named after Native American tribes with sort of similar sounding names, but they're not actually connected. But I will say, even though they are the more famous Miami as far as schools go, we were established somewhere around 1809, which I recognize is still relatively modern by like European standards. But University of Miami was something like 1925. So we're much older than them, even if we're less famous. But to make things even more confusing, the town we're in is not Miami, Ohio. There isn't one as far as I know. But it's in Oxford, Ohio, which is really confusing. But it was a planned college town. They wanted it to have a university sounding name. I don't know. Anyway, but I didn't intend my whole lecture to be a geography lesson, but I just thought I'd point that out because, like I said, even here, people here in the States get this wrong. Okay, so I'll mention a few of my collaborators. The talk I'm going to the paper I'm going to focus my talk on is primarily this paper about reflection groups and rigidity of quadratic Poisson algebras. And that's with Padmini Virupin, who's at Tennessee Tech, and Jingting Wang, who's at Louisiana State University. But I may get a chance to talk about some of these other related papers. One of them is on the Zariski cancellation problem for Poisson algebras with Jingting. And the other one is this other cancellation paper with Dan Yi, who's at Bradley University. Yeah, so I apologize to Dan. I didn't have a better picture, so I stole one from like a conference photo. Okay. So what am I going to talk about? I'm going to talk about Poisson algebras, and I think I'm probably at a setting where I don't really have to define this, but I probably should just to be thorough. I'm always going to work today, at least because it's a talk, over a field that's algebraically closed in characteristic 0. Not every result I mention needs both of those. I'll refer you to the paper for details on that, but it's safe enough assumptions for everything I'm going to say. So Poisson algebra is an associative commutative algebra A. In many, if not all of my examples today, this will actually be a polynomial ring, but that's not strictly required. And then a bracket such that makes A into a Lie algebra. And then each element of A should define a derivation on the algebra A. These are sometimes called the Hamiltonian derivations. Another way of saying this is that the bracket is actually a biderivation. because you have skew symmetry, then you get a derivation in the other component as well. And then a Poisson homomorphism is just a map that between Poisson algebras that respects the bracket according to this rule. And a Poisson automorphism is just a bijective Poisson homomorphism from A to A. And now I'm going to mention a pretty famous theorem, but one that's a basis for a lot of what I'm going to say here. So recall that a reflection of a polynomial ring is just a graded automorphism that fixes a codimension 1 subspace. Another way of saying this is because thinking of it as a linear map in computing its eigenvalues, it's saying that the eigenvalues are all ones, and then 1 is some root of unity. So that's a reflection. And then the Shepard-Todd-Chevalley theorem says that if you take invariance of a polynomial ring by a finite linear group, it's again a polynomial ring, if and only if the group is generated by reflections. So I want to think about this theorem in the Poisson setting. Now, here's the thing. Maybe this is completely trivial because, so let's just take the case where we have a polynomial ring with some Poisson structure on it, some bracket. And then you take some Poisson automorphism and you do this cute little computation. So if you take 2 elements here in the invariant ring, what we notice is that, well, just by definition of a Poisson homomorphism, the bracket's preserved. So if you have 2 things here in the invariant ring, their bracket is also in the invariant ring. So that means that if you start with this A, that AG also has Poisson structure. And so you could sort of say that this is all, just asking whether or not the invariant ring is Poisson algebra is almost completely trivial. It just comes from, if you just want it to be polynomial, then the answer is just the Shepard-Todd-Chevalley theorem when your Poisson automorphism group is generated by reflections. But I want to ask something else. I want to sort of dig into the different structures that maybe you could put on a Poisson algebra that a Poisson algebra could have, or different properties that the algebra could have, and ask which ones of those are actually preserved by taking invariance or invariance of a certain type. And my starting point for this is going to be what we call skew symmetric Poisson algebras. So here's what I mean by that. So take a polynomial algebra with a Poisson bracket. There's a natural grading on A, right? Just the natural, I say natural grading, I mean the natural n grading on the polynomial ring. Degree 0 is the field, degree 1 is the vector space generated by the generators. And then in degree n, it's the vector space spanned by the degree n monomials. All right, that's all we have. So we say A is quadratic if the bracket of any 2 generators lives in A2, so the generated by degree 2 monomials. And a quadratic Poisson polynomial algebra, so an A here, is skew symmetric if, more specifically, whenever you take the bracket of 2 of your generators, you get the product of those generators, it's commutative, so order doesn't matter, but multiplied by some Qij. And these are scalars, they can be 0, but the rule is that essentially they have this rule that Qij is negative Qji, so obviously what that means is that the matrix with these entries Qij is an honest skew symmetric matrix, and hence the name. And so a Poisson reflection now is simply a reflection that is also a graded Poisson automorphism. And I'm going to go ahead and give away the big theorem here, but then give you some information behind it, and then sort of some further questions from it. That if you start with a polynomial algebra with skew symmetric Poisson structure on it. And you take some finite subgroup of graded Poisson automorphisms of A. So that means that they're essentially linear maps on the degree 1 piece. And they're also Poisson homomorphisms. Then the invariant ring has skew symmetric Poisson structure if and only if G is generated by Poisson reflections. So this is suddenly now a non-trivial theorem because we're not just asking if it's a Poisson algebra, but we're asking that the generators of the invariant ring behave a certain way. And this is a natural analog of a theorem that was proved by Kirkman, Kuzmanovich, and Zhang in the associative setting. So they were looking at what you might call skew polynomial rings, or they might be called quantum affine space. There's a lot of sort of natural analogs between results in the associative non-commutative setting and in the Poisson setting, especially for these graded things. And even though there are natural roads to go between non-commutative algebra and Poisson algebras, so for example, going, you can go from a Poisson algebra to a non-commutative algebra by quantization. But there aren't a whole lot of results that connect the sort of ring theoretic / Poisson ring algebra theoretic properties directly. So we want to understand these things, but it's not simply just taking their theorem and sort of turning there's not sort of a natural road between it, even though it's a similar theorem. Okay. So one direction, so I want to talk about the proof of this theorem just a little bit. One direction is easy. It is just implied by the Shepard-Todd-Chevalley theorem. So if the invariant ring we know has skew symmetric Poisson structure, that means the invariant ring is a polynomial ring. So Shepard-Todd-Chevalley says that our group of Poisson automorphisms must be generated by reflections. And they're Poisson maps, so they're necessarily Poisson reflections. So what we're really interested in is the other way, and that comes down to sort of a firm understanding of what these invariants look like. Okay, so let me start off with an example. So this is sort of an easy example. It's just, but it's the simplest non-trivial one that we can do. So this is the degree or the two variable case. So we've got two variables, polynomial ring, two variables. We've got the bracket, xy is some scalar pxy. I restricted p to not be 0 here just because then you don't have an honest Poisson structure, right? It's just the trivial one. So it's true, but then you're just using Shepard-Todd-Chevalley. And let's take a Poisson automorphism. So then it turns out, I didn't say graded, but it turns out that in this case, these are all the Poisson automorphisms look like this. But certainly if you restrict to the graded case, then it's just a little easier to check this. So there's some scalars that you can scale the generators by here, or maybe you flip the generators. But it turns out that the second one doesn't really work. If you're looking for a reflection, because what happens, well, you scale by both of them over here, you multiply G, but then you apply the Poisson structure, and you end up with negative that. I'm working characteristic 0. So I can restrict to either case, but so the second one doesn't happen. So I have to go here, but then I get two cases if I want a reflection. If I want a reflection, one of my scalars needs to be 1, and the other one needs to be an nth root of unity. So let's assume that nu is 1, and mu then is just an nth root of unity. Now it's not hard to check that the invariant ring is just generated by some power of x and by y, because y is fixed. And we can look at what the Poisson bracket gives. And what it gives is really, with my generators, it's still got skew symmetric structure because this is still just some non-zero scalar here. Okay, so that's the basic idea, but once you go up to even 3 variables, it becomes a lot harder to say what exactly the invariants look like. You can't write down what well, you can write down what the reflections are, but you don't know what the reflection groups look like quite as easily. So here's sort of the strategy for it. Let's take a skew symmetric Poisson algebra. So I'm assuming we have this structure. Bracket n is just going to be my shorthand for the set 1 through n. And this should say for I in n, the block of I. So here's the definition of the block B sub I, right? And it's defined in terms of these the parameters that show up. What this is really saying is that I and I prime are in the same block if and only if the rows of the matrix Qij, the ith row and the I primeth row, are exactly the same. All right, so they have the same row. And another way to think about that is that all of these, the generators here, the xi and the xj, they're all Poisson normal. So what's Poisson normal? So A is Poisson normal if if this always lands in the ideal generated by A. So of course that applies to all the xi here. But if you have a domain, then really what this does is it defines some sort of derivation, right? So it means it looks something like that. So it's saying that xi and xi prime here define the same derivation like this. So this gives us an equivalence relation, and then we can split up into our equivalence classes. We can take a representative from each equivalence class. So that's my W here, a complete collection of distinct representatives. And this gives us a decomposition of N into blocks. And so we're going to use this to talk about our to sort of give an understanding of what the invariants look like when we take invariance by Poisson reflections. So let's take a skew symmetric Poisson algebra again and do the construction we did before. We'll take some representative here. And now this notation is all my graded Poisson automorphisms, or Poisson graded automorphisms. I'm not sure which way I'm supposed to put those adjectives. We'll say graded Poisson automorphisms of A. And this then is going to be some subgroup of that. And the way it's defined is that, okay, a theta is in there, is if for all the S not in BW, it's just going to fix them. So it's not going to do anything to those. The only ones it acts on are the ones that live in that particular, or their index lives in that particular block. Right? And then it's going to be sent to some finite linear combination of those. And then what you can prove is that every Poisson reflection belongs to this subgroup. So now we can do a bit of a decomposition of our Poisson reflection group G. So we'll take G sub W to be the intersection of G with this subgroup relative to W. And then you need to prove a couple things, which I'm not going to do here, but you prove a couple things. First of all, that each generator of G belongs to exactly one of these. Now, G is generated by Poisson reflections. That was the definition. It's not automatic, but it's also not hard to prove then that each GW is generated by Poisson reflections, and that this actually gives you a decomposition of G. So let's just take the case that, just for simplicity, that W is 1. So the block then is 1 up to some k. It might just be 1, but it's 1 up to some k. And then that means that x1 through xk generate a Poisson subalgebra of A, which we denote AW. And so now what you can check is that, well, the group GW, all right, go back up to the definition up here, that it only acts non-trivially on the xi where the I belong to that particular block. So that means that the invariant ring just looks like the invariant ring of this AW, and then it leaves everything else alone. And now what you can do is you can apply, this should have a little W here, that AW, GW, well, now we're just applying the Shepard-Todd-Chevrolet to get a list of generators for that, homogeneous generators in x1 through xk. They all have the same degree. And, no, I'm sorry, they're all homogeneous, but they don't necessarily have the same degree. So if UI has degree DI, and they all Poisson commute with each other. But how does UI act on one of the xj that essentially lives in here? Well, it acts the same way that if we go back to our example, it acts like the xm does here. Right? It just uses the derivation on that. So you check that you just pick up this DI. All the UI come from the xi, and the x1 through xk all act the same. That was the point of being in the same block. So we get Q1J here because we included 1, UI xj. Now what we do is we use the fact, so that sort of proves that if GW was all of G, then you're done. That's it. But most likely you have a bigger decomposition here. So you have multiple of these things. But if you take some W prime that's distinct, the prime here should be here. If you take a W prime that's from a different equivalence class, then GW prime and GW commute. So that means that GW prime acts on a fixed by GW. And so now the process just continues. Now you just take your next one, you act on that, you just keep doing this inductively, and then you're done. So that's a sketch, at least, of how the proof works. Block decomposition is sort of a useful trick. Okay, so let me come back to my example just to extend this a little bit. So what happens? We had a polynomial ring and 2 variables. We had a skew symmetric structure on it. We took invariance. So now I'm calling my invariance X and Y, capital X and capital Y. And here's the bracket on it. And M is greater than 1, because otherwise this is kind of trivial. very trivial. And so then it turns out that one can show without much effort that A and its invariant ring are not isomorphic. Now here's the thing. In the commutative world, so we're just working with a polynomial ring. I mean, it's not always stated like this in the normal statements of Shepard-Todd-Chevalley, but in that case, I mean, the point is that AG is a polynomial ring in the same number of polynomials, so it's actually isomorphic to the algebra you started with. Right? So this is what happens when you're working with a commutative thing. But it turns out for non-commutative algebras, that's actually very rare. One of the first examples of this, and this will come up again in a few slides, was a result of Paul Smith looking at invariance of the first Weyl algebra. And there's been lots of extensions of this, but it turns out that invariants of the first Weyl algebra are never isomorphic to the first Weyl algebra. In fact, there's a more recent result by Tikaradze that the Weyl algebra isn't the fixed ring of any domain over C. But right, so the point of that is that when you're working with non-commutative algebras, you don't necessarily expect this result that comes from the Shepard-Todd-Chevalley theorem. And in the Poisson world, it's the same, right? That we're getting back an algebra with the same structure, but we're not getting back the same algebra. In fact, they're non-isomorphic. And the way you can prove this, it's not hard to do it directly. But in fact, it's very easy if you apply this theorem, which again has an analog in the associative non-commutative setting by Bell and Zhang. What it says in the Poisson setting is that if you take two connected graded, so connected, what does that mean? So we're looking, when I say graded, I mean n-graded. Connected means that the degree 0 part is just the field. So two connected graded Poisson algebras, finitely generated in degree 1. If they're isomorphic as potentially ungraded Poisson algebras, so there's just any Poisson isomorphism between them, then they're actually isomorphic as graded Poisson algebras. You can find a graded map between them, one that sends the degree k speed space to the degree k space. There we go. Right. So you can reduce this problem to just looking at the graded structure. And in fact, what you can show, where can I squeeze this in? That if A is like the above, so let's say xy is pxy, and then you got some B that's, the same thing, but a different Poisson bracket, potentially. But potentially some different scalar there, that these are isomorphic. So A is isomorphic to B if and only if P is plus or minus Q. All right, that was really sloppy. Let me fix that. P is plus or minus Q. Okay, but M is not going to be 1 or -1. So that proves that they're not isomorphic. All right, like I said, using this theorem, this is a trivial exercise. Okay, so a question we have, which I think is true, but I realized we didn't actually prove it in our paper, and then I'm not sure I actually know how to prove it. In full generality, though, like I said, I'm pretty sure it's true. that if you take a polynomial ring that's got skew symmetric Poisson structure on it, and a finite subgroup of Poisson automorphisms, then, okay, the theorem says that this will also have skew symmetric structure also, but that AG will not be isomorphic to A unless G is just the trivial group. So that's the conjecture. I'm pretty sure that's true, but I don't see how it's immediately implied by what we did, except, obviously I just explained to you why it's true essentially in the n=2 case. Okay, but this idea, so this is what I think of as rigidity. At least it's one version of what one might call rigidity. That you're taking invariants, and the invariants are somehow different than what you started with, which is a almost purely non-commutative phenomenon. So we'll make this a definition, and I'm going to define this both in the graded and non-graded setting simultaneously. You take a Poisson algebra and a finite subgroup of now just Poisson automorphisms of any kind. Then A is graded rigid. If an isomorphism between the invariant ring and the algebra you started with implies that G is trivial. And okay, so we saw this happen with the skew symmetric algebras, at least when n=2. Here's another example, which I'm not going to do in a lot of detail. I'm going to sort of go through several examples. So take any finite dimensional Lie algebra and take the symmetric algebra on that, so the polynomial ring. And you can define a Poisson structure then by just defining the bracket of x and y to be, well, to be the bracket, but the Lie bracket of x and y. And then you can extend that to all of SG using properties of the Poisson bracket. And this is called the Kostin-Kirillov bracket. I've seen it have a few other names, but I don't remember what those are. This isn't quadratic, though. I mean, you can certainly ask the question for this, but I'm sort of interested at the moment in homogenized structures because these are quadratic. So to do that, I'm going to introduce a new central element, T. So Poisson central. So of course that just means that bracket of T with anything is 0. And so the associative structure, I'm just doing a polynomial extension of this with T. And then the way this is defined is, okay, so T is Poisson central, and then the Poisson bracket of x and y is the Lie bracket, and then homogenized by multiplying by T. So this will be either 0 or it'll be something strictly of degree 2. And then what we can show is that if G has no one-dimensional Lie ideal, then this homogenized algebra, Poisson algebra, is graded rigid. It fails, I believe, in here. And there's an example in the paper that shows that you do need this hypothesis. Okay. Here's another example, which I'll go through quickly. So you can take the ring of n by n matrices and then take the ring of regular functions on that, but that's just a polynomial ring. And you get, there's a natural Poisson bracket on this, and the way that this arises is through the process of semi-classical limits. So semi-classical limits is one way to go from the non-commutative algebra structure to Poisson algebras. Both directions are really related to deformation theory. And so what are you taking the semi-classical limit of? Well, you can define these quantum matrices, these rings of quantum matrices. Take semi-classical limits of that. So in this case, okay, what are we asking? What do we really mean by asking if it's graded rigid? So I want to take this Poisson algebra, right? And I want to ask, is it isomorphic? But I'm still dealing with polynomial algebras. So I'm still in the setting of Shepard-Todd-Chevalley. So I still care about Poisson reflections. And so in this case, actually, when n is greater than 2, you can show that there actually are no Poisson reflections there. So it's sort of trivial. I mean, it's not trivial to show that, but once you show that, the result is automatic. So the only thing to do really is in the case of n equals 2, in this case, there are reflections, but you can compute precisely what they are. And then you can compute the invariant ring explicitly and prove that it's not isomorphic to the algebra that you started with. It's got a different bracket structure on it. And then I think more or less my last example on this topic is the nth Val-Poisson algebra. I remember having a vigorous debate with my co-authors, which I lost, on whether it's Val-Poisson or the other way around. I thought this was wrong, but as I said, I lost, so I should stick to the convention that's in the paper. Okay, so this is a Poisson polynomial algebra in 2n variables. This mimics the associative Weil algebra, right? So the bracket of xi and xj is delta ij. This is the Kronecker delta. And then, whoops, that is wrong. Xi yj is delta ij. And, but if you bracket xi with xj or yi with ij, then it's 0. Okay. This is, you can put a z grading on this, and there's a lot of ways to exploit that z grading, but it's not n graded. We can make it n graded by homogenizing, but I should mention first that there's a result that was actually brought to our attention by Tikaradze, semi-unpublished, sort of like putting together a few of the things that he had already published. So there's a note in our paper that you can prove rigidity for this by sort of piecing together a few of the things from his papers. That this is actually rigid. And as I mentioned, sort of the best result in this direction, at least in characteristic 0, is due to him in the associative setting. So what we formally looked at in our paper was this homogenized version. So let me fix my copy paste error there. That's a yj. Right. So xiyj is, okay, so now it's still delta ij, but we homogenize that with the z squared. So that's actually a quadratic term. And then everything else just Poisson commutes. And again, you can compute the reflections of this thing explicitly. And the only non-trivial Poisson reflection groups are actually order 2. So if you take some non-trivial thing, you can compute what this looks like pretty easily and show that it's not isomorphic to the one you started with. So again, it's graded rigid. Okay, so I think that's the last concrete example, but I do have one more family of examples to talk about. First, I need a definition, though. So take a Poisson polynomial algebra, pick a bracket. You can define the modular derivation of this. I only know how to do this really in the polynomial setting. And so here's the definition. So you're taking some partial derivatives of the bracket of x with all the xj. all of your generators, and then taking the partial with respect to xj, add them up. And then we say that A is unimodular if and only if this modular derivation is 0. And this is closely connected to the Calabi-Yau condition for associative algebras. And one way it's connected is this result. I think it's due to Jingting Wang and his collaborators, but I've not remembered which paper that was exactly. The A is unimodular if and only if its Poisson enveloping algebra is Calabi-Yau. And I don't have a definition on this, but you can think of it as, I mean, like you would any enveloping algebra. It's some sort of associative algebra that here captures both the associative and the non-associative structure of a Poisson algebra. So it's actually much bigger than A itself. It's like twice as big. So the GK dimension actually doubles for this thing. But this is how it's connected to Calabi-Yauness. And then there's some results for which I don't have great citations. They're probably in the paper. But I should have put them on the slides. So in the two variable case, A is unimodular if and only if A is the Weil-Poisson algebra. If A is a polynomial ring in 3 variables, it's unimodular if and only if there's this potential. So there's some F potential, and the bracket is just given by all these like partial derivatives. So the bracket of x, y, so it's just cyclic, right? X and y, their bracket is the partial of f with respect to z. Y and z is the partial of f with respect to x, etc. This goes by a few different names. Might say it has Jacobian structure. They're also called exact Poisson algebras. So they go by a handful of names. In the commutative set, or not the commutative, in the non-commutative setting, sometimes we call such things like derivation quotient algebras or something like that. Okay, but I only really care about the potential, so I'm just going to refer to these things as Poisson algebras with potential. So let's take a specific potential here, and generically, and by generically I really mean when P is non-zero, really what I mean, A has no Poisson reflections. And so this thing is trivially graded rigid. If P is 0, and for certain Q, there are cases where it has Poisson reflections. And then what you can prove in that setting is that if you take invariance by Poisson reflections, you actually get another Poisson algebra with, let me back up. In this case, they're all ones with skew symmetric structure. If P is 0, it's not hard to see that. So for example, you just have, really you're just in the case that F is QXYZ. So you're just taking the partial with respect to Z, and you get something in terms of X and Y. And then that works for all 3 of them. So you're just getting skew symmetric structure. And now we can apply our result before, that we get something again with skew symmetric structure, but we can check in this case that it's not isomorphic to what we started with. But since our papers come out, there's actually a more general result out there. As far as I know, it's just a preprint, but it seems to check out. It's a lot of basically goes through the full classification of potentials and the automorphisms and computes their Poisson reflections explicitly. Lots of details by Chengwan Ma, who's currently a grad student at University of Washington. And his result is that if you have any unimodular quadratic Poisson algebra, and G is a finite subgroup of Poisson automorphisms, then A is graded rigid. So it's sort of, we did a very specific potential or family of potentials. He did all of them. Okay. So I only have about 5 minutes, and that's fine because I was just going to mention really that another way you can think about rigidity is this Zariski cancellation problem. Of course, this comes from the commutative world, where you can ask, well, I think the original one was stated in terms of field extensions, the original problem posed by Zariski. But in the geometric sense, you can say if you take an affine variety and you extend it by affine space, does that imply an isomorphism here? And then, so if you want to generalize it, you could go to a non-commutative algebraic variety. This is the setting of Artin Shelter regular algebras. That's not what we're doing. I'm going to think of Y as an affine Poisson variety, but I don't want to do this geometrically. I want to do this in the algebraic sense. So I'll take the algebraic definition of cancellation. So that's why I think of it as sort of a rigidity type result, because you're asking if an isomorphism of extensions implies that the original things are isomorphic. For algebras, I mean, this is a very famous open question. Like, this is, I don't know, Fields Medal territory, maybe, for those that are young enough to still be considered for a Fields Medal. So it's known for polynomial rings of 1 and 2 variables. But in characteristic 0, it's still open for n greater than or equal to 3. In positive characteristic, it's not true in 3 variables. I'm going to skip this slide and just go to what are we asking? So under what conditions is a Poisson algebra a Poisson cancelative? And here's one setting. I'm not going to go through the whole proof. I mean, this is in my paper. I was spelling these out before with Chingting. So one case where if you have a Poisson algebra with trivial Poisson center, then it's Poisson cancelative. That's a short proof that I would do if I had more time. And it's actually universally Poisson cancelative. What do I mean by that? Well, you can think of the polynomial extension, right, as tensoring with polynomial ring in 1 variable. So here, all we mean is a tensoring with some commutative domain. So in fact, this works in that setting as well. And the result that I'll just mention without all the details is to show that quadratic Poisson algebras on 3 variables are cancelative, are Poisson cancelative. That's sort of implied, right? And the primary method that we used, without going into too many details, is this idea of discriminant ideals. So you're taking the Poisson center, so things that Poisson commute with everything else, and defining some property on the maximal ideals of that Poisson center. Now, that's actually, honestly, a commutative algebra because the Poisson bracket on the Poisson center is trivial. So this makes sense to talk about max spec. I don't need to restrict it to Poisson ideals or anything. And so you define some property in terms of that. And then skipping many, many details, you can actually prove that. And the exact properties we use, maybe I'll go back 1 slide real quick. So we have this classification of really, this isn't all structures on a polynomial ring in 3 variables by any means. But this is all the ones with the structure that X and Y gives some polynomial of degree 2 with a Poisson central element T. One of your generators is actually Poisson central, and you have all the structures there. And so what we were able to do is sort of go one by one, more or less, and pick out some structure or some property on max spec and break them down that way and prove that we can actually get all of these to be Poisson cancellative. And here's a few other families that we were able to do. I won't go into these too much. These were the same constant Kirillov brackets. That's sort of another one of these classification problems, sort of one by one through these things. And I think I'll stop there. Thank you very much for listening, and I'm happy to answer any questions.
Thank you very much, Jason, okay, for your interesting talk. Okay, we have some time for comments and questions. Welcome. Maybe I can ask, because I'm not expert in this area, but when you was talking about this cubic potential F in 3 variables, that's some result about if P is not equal to 0, it should be rigid and something else. So I'm just curious, okay, so for P equal to Q, this polynomial is reducible. Does reducibility have something to do with the property to be rigid or not? I think not, maybe, okay.
So in this case, I mean, in this case, they're all rigid. It's a question of whether or not they have any Poisson reflections. So that's really the only difference between the two cases, is that when P is non-zero, you can just show that you can show directly that there's no reflections of this thing, and so you don't have to do any work. When P is 0, then you just get skew symmetric structure, but then you can compute the invariance directly. So it turns out to not be too hard. Your question was, what about when like P equals Q?
Yes, right, because it will be reducible, right?
Yes. Yeah. I don't think we had to use that at all. Certainly, certainly you could simplify the potential, and there's probably an easier way to do it directly in that case. But I don't think we had to look at that as a special case. I think we were able to just show, if I'm remembering correctly, I think that just fell into this case, that as long as P was not 0, then you can just, there's no reflection. So we didn't do anything beyond that. If I'm remembering correctly.
Other questions, comments? Okay, let us thank you again, Jason. Okay, thank you very much. And now, okay, I can give maybe some last words to the organizers. Jabir or somebody else will say something. Either? No, then we have to, yeah, thank you, everybody, of course, again. Have a nice day. Okay. Many nice talks. Yeah, we have to finish this Non-Associative days. Thank you for organizers, for everybody. Thank you again. See you.